All right, this video is going to be on the logistic differential equation. So the logistic model that we are going to work with is dp dt, which equals k times p multiplied by 1 minus p over c, and this is the standard form. So that will be important to know because we'll refer to that. So K is going to be your relative growth rate again. And C is the carrying capacity. So if you guys don't remember what logistic functions look like, logistic functions had two horizontal asymptotes. The lower one is always 0, and then the upper one is the carrying capacity for the population. So that would be like, based on, if we're talking about monkeys that are like living in the jungle, that would be based off of how many predators are there and how much room there is for them for all the resources they need. You couldn't have infinitely many monkeys. You'd run out of space and you'd run out of resources. So the carrying capacity is like the maximum that you can have. Any more than that and they'd start to die off. So relative growth rate, carrying capacity, P is the population. So here, these are only going to be recognizable if the formula, if the model is given in the standard form. If it's not, you're going to have to factor it. If you can see, these kind of look factored. So if it's not written like this, you have to factor it out. But once it's written like this, you can recognize what those numbers are just by looking at the number in front of P to find the K and the number underneath P over here to find the C. So equilibrium solutions are described as when dp dt equals 0, so when there is no growth to the population, and this is going to happen in two places. So I'm just going to go ahead and write out these factors. So that would be when these factors equal 0. So the first place is over here. And so we're going to say Kp equals 0, and if we divide by that constant K, we're going to get P equals 0. So when the population is 0, it's going to stay 0, which kind of makes sense. And then over here, we're going to say 1 minus P over C equals 0. So that means that 1 equals P divided by C. And if I multiply the C up to the other side, when the population is at the carrying capacity, then it is likely to stay there. That's an equilibrium solution. So that means the population's not going up, it's not going down, it's going to stay pretty constant. When is the population growing the fastest? The answer to that is when you're at 1/2 C. So you're halfway between, you can see it in a logistic function right here in the middle. It's when you're halfway between 0 and the carrying capacity. That's when the growth is the steepest. So we can definitely see it by looking at the graph itself. You can also solve that using derivatives. So we're going to say that the differential equation is dp dt equals kp minus kp squared over c. So what I did is I just went ahead and I took that standard form and I took the kp and I distributed it. And since I'm looking at growth rate, the instantaneous growth rate, I want to take this and find the second derivative of this function. So that's going to be d2p dt squared. So the derivative of k times p would just be k times the derivative of p, whatever that is. So this is going to remind you guys kind of when we were doing the problems that had the derivative of y, and then we wrote a dy dx in there, if you guys recall that. The derivative over here of this part, we would drop the 2 to the front. So minus 2kp, and that p is now an exponent of 1 divided by c. And then the derivative of p is dp dt. And we would know that that would equal 0. So here I'm going to go ahead and factor this that I have right here to solve it. So I can see that there's a common factor of dp dt, and there's a common factor of k as well. So I'm going to go ahead and take those out. And then left over, I have 1 minus 2p over c equals 0. And I already know this factor in the front is going to be 0. That one's not very exciting. So the one that's going to help us prove that the population is growing the fastest at 1/2 c is if I take this one and set it equal to 0. So 1 equals 2p over c. I'll go ahead and multiply the c to the other side. C equals 2p. And then when I solve it, the population is growing the fastest for c over 2. So again, if that algebraic explanation didn't make sense to you, you can just picture looking at the logistic function up here, and we can see that it is the very steepest right there in the middle. All right, what happens as to the population as time goes on? Can you set up an equation that represents the situation? So if we look at this population, this line, as time goes on, so as we're going to the right on the graph, because time is the x-axis, as time goes on, the population increases, and it gets really close to that carrying capacity. So we're going to say it approaches the carrying capacity. And when we write this as an equation, we're actually going to think of it as like a limit. So I'm going to say the limit as t goes to infinity, so as time goes forever, of the population in regards to t, in terms of t, is going to be c for the carrying capacity. So the population approaches the carrying capacity as time continues forever. What happens to the rate of change as time goes on? So as you get closer and closer and closer to that carrying capacity, this population here flattens out to a horizontal line, right? You're approaching a horizontal asymptote. So as you get closer to that carrying capacity, your rate of change is going to get closer and closer to 0. Once you hit the carrying capacity, you're at an equilibrium solution, and your population is not going to change much anymore. So we're going to say it approaches 0. And if we write this as an equation, we're going to do the same thing. We're going to represent it as a limit. So we're going to say the limit as t goes to infinity of that derivative, so of that rate of change there, is 0. All right, so for example, we have dp dt is 0.25p multiplied by 10 minus p. And so what we want to do first, before we can look at this example at all, is we do want this to be written in standard form. And I can see that it's not, because this is not a 1 right here. So if you look up here, it should be 1 minus p over c. That has to be written as a 1. So for this to be able to be written as a 1, that means I have to divide 10 out of those parentheses. So my standard form is going to be 0.25 divided by 10p times 1 minus p over 10. And not divided by 10 out here. We would have divided by 10 inside the parentheses, so that means outside the parentheses. We would have been multiplying by 10. So that would be 0.25 times 10. And I'm going to go ahead and write it there like that, so that if I look at my notes later, I can see what I did there. So that means that this value right here is the k value, and that value right there is the c value. So k is 2.5, and c is 10. So now I can go ahead and look and see what my equilibrium solutions are, since it's in that standard form. So my equilibrium solutions are going to be 0 for this part, and 10 for this part, so 0 and 10. And the population is growing the fastest at c divided by 2, or half of c, so it's growing the fastest at 5. And we're going to go ahead and draw a little sketch in here. So we have a horizontal asymptote at 0 and a horizontal asymptote at 10. and we're going to say that our equilibrium solutions are there, right? So that's where it slants, that's where we have a slope of 0, so that's why we're seeing those as horizontal asymptotes. And then when we look, we're going to see the very steepest slope right here for drawing our slope field, and then we're going to see slopes that are less steep here, and even less steep here. And then you can see if you were to follow these curves, we could start like right here and we'd be able to follow it up and see that it goes like that. So it looks like a logistic function. Okay, if we look at the other side of our notes, so remember the relative growth rate is that K value, so that's the number that's in front of P as long as it's in the standard form. Equilibrium solutions are where the factors equal 0. And it's growing the fastest when you have 1/2 of C. All right, so this one is written in standard form, so we know that we can just pull those numbers out of there. So the K value is 1/100th. The equilibrium solutions are going to be 0 right here and 250. So your equilibrium solutions are basically always going to be 0 and C. And then it's growing the fastest at 1/2 C, so that's 125. This one is not written in that standard form. So for us to fix this, we have to divide the inside of the parentheses by 2. So it's going to be a 1 minus P over 1,000. And then in front of the parentheses, we have to multiply by that 2 that we took out. So that's going to be 0.004 P. So that relative growth rate is the 0.004. The equilibrium solutions are going to be 0 and 1,000. It's growing the fastest at 500. For this one, there is a typo. I didn't realize that I missed the P right there. So there should be a P right there. That was my bad. So the relative growth rate is 1/250,000. The equilibrium solutions are 0 and 100,000. And it's growing the fastest at 50,000. Over here, this one is not written in that standard form, so I know that when I write it in standard form, it should have a 1 right here, 1 minus something. So that means that if this part is going to become the 1, I have to divide by 1.5p. So 1.5p belongs in the front. And if I take 0.003 and divide that by 1.5, I get 1/500 as my fraction. So I have P over 500 when I factor that out to get that standard form. So that means that my relative growth rate is 1.5. The equilibrium solutions are 0 and 500, and it's growing the fastest at 250. And we will go ahead and fill out the rest of the notes when I see you guys in class tomorrow.